Is the red light on? There we go. What I'll tell you about this. So I'm on page 10. Page 9 is pre-recorded. This page is going to blow your mind, and if it doesn't shock you, so Niels Bohr, like one of the geniuses in the past in human being, said, if you're not shocked when you come across quantum theory, then you don't understand it. So you should be going, what? Because this breaks all the laws. They actually told Max Planck, Niels Bohr, their parents and stuff said, oh, go play the violin. Everything's been figured out. And thankfully, they didn't listen. So I'm going to walk through these steps on this page. I'm going to do it on the board so I can talk big. And then I'll come back and we'll go through electron configurations. Keep in mind, it's like with the moles. When you first heard it, you're like, what is she talking about? That's why you have study sets. And so do the study set as best as you can. You're going to miss the math because there's a lot of questions that you just have to go with it. And when we go over it, it will start clicking. And then we do review on Wednesday. Wednesday's all about review. So just bear with me. And this ends up being most students' favorite part, but not tonight. It's like Wednesday once it clicks. So just do the best you can with following along. All right. So there are shells. There's 4 levels that we're going to go with. And this all has to do with color. I couldn't wear my rainbow squid hat because I didn't want to catch it on fire when I did the fire. But I get to wear it because it's an electron. So Tiffany's probably jealous because I have a rainbow squid hat. But I didn't want to wear them. I didn't want to catch them on fire, which I would have done. I've caught myself on fire enough. All right. You guys have heard these things. And again, if you can't see me, let me know because your view is different. So we have shells.
It is kind of like bright, right where you wrote.
All right. Well, I'm going to do it over here. Is it bright over here?
No, not at all. Yeah.
Okay. You have the word shell. The shell is designated by the letter N. It's always written as kind of a funky cursive font. N is, the shell is the distance from the nucleus. And what we're talking about here are electrons. Where is the electron? So you know those games, Where's Waldo? This is what this is. We're going to figure out where the electron is. And there's been so many Nobel Prizes that were given to figure this out. So the shell is typically what you've all heard of before or seen before. That this in the center is the nucleus, right? Remember, this is the positive little nucleus. And the electrons are orbiting outside. But there's a couple layers to how they orbit. And so they can be in these different layers. So these are electron orbits. These are the shells. So this would be N equals 1, the first layer, N equals 2, N equals 3, and so on, and so on, and so on. So N is a whole number. And I often talk about this. This is like an apartment. So it'd be like what layer or floor you're on. So the first layer is the closest. So as you increase the N, you increase the distance. So layer 1 is the closest, then layer 2, and then layer 3. You cannot be in between. And so that's the whole idea of a quantum leap. I can only be here or there. This is what Star Trek figured out when they beam them up, is they're doing a quantum beam. So they could only be there or they could be up there. And you can't be in between. The thing that's really cool is they've actually started figuring this out. And probably within a decade, everything's going to be very different from what you see now. All right, So that's the N. The other thing with the N is as you increase N, you increase the electron's energy. So as it gets further out, it's more wound up. The reason for it is it's got a bigger distance to go around. So like if I had Tiffany here on this first track, she can take her nice sweet time because she's on a nice small track. And then if Tatum, I put her out here on N equals 3, she's got to really be moving. So she's got to have a lot more energy because it's a much bigger shell to go around. So that's the first layer. There's nothing too bad about that. So the next layer is called the subshell, or the next piece is called the subshell. And the subshell, rather than numbers, they gave it letters. It actually comes from a mathematical equation and they changed them. And the letters are S, P, D, and F. And you guys, not only does your teacher's birthday happen to be Hydrogen Day, but your chemistry teacher's name is Sherpa, and everything I post for you is a PDF. So the order is really easy to remember. It's a Sherpa PDF. Plus, you guys are allowed a cheat sheet, but just remember that order. And this is always, what the subshell is the shape of the orbital. And at the end, when we get there, we'll take a quick look at some of these shapes. S is a sphere. So this is a sphere. Now, you can always go back that everything is an S. If what we get to, you're like, how can that be? So these were all S's. This would be, in fact, called the 1S, the 2S, and the 3S. So it's an address. Everything gets an address of their shell and their subshell. So what layer they're at, so what floor they're on, and what shape they are. A P looks like a figure 8 or an infinity sign. Or, I don't know, what other ways can you do it? A D looks like a 4-leaf clover. And an F looks like an 8-leaf clover. You can try and draw it. And actually, it keeps going. But we're just going to stay with this PDF. So back to the question I mentioned earlier. As you move out, you get higher energy. As you go more complex shape, that means it's got more energy. And this is, I don't know if I just got off my board, but I guess you can see it. Yeah. So again, if I had, you know, Tiffany's in here running her 1S, that's really nice. And so Tatum, not only do I have her out there running in the 3rd level, I'm making her run a D. She's going to be going crazy. So you have, everything has a shell and a subshell designation. So 3D means she's 3 levels out and she's running a 4-leaf clover. So it's like, how can this be? Because they all start running into each other. Electrons never run into each other. Never. That's the magic of it. So if you ever don't like this, just say it's all like fairy dust. And it really is. All right. The next thing it says is something called the orbital. And that is the electron's path. So what does its path look like? Niels Bohr originally called it an orbit. All of his math was done with hydrogen, which has only 1 electron. He broke the barrier that everyone now thought about this totally different. And so they changed the word to orbital to explain what they often call the new quantum mechanics, but it's all the same thing. The piece that people don't like here is there's one more word, which is probably. You can never know any of this for sure. And what I said in the in my pre-lecture, the easiest way to think about it is quantum mechanics explains actually why we have computers, why we have cell phones, why we have calculators now that are like super duper amazing. It's how our brain works. And it's why your cell phone will stop working when you need it to. It like gets all mixed up. And it's because the electrons just need to go to reset. Because all of this is based on probability. All right, we're going to add one more piece, which is electron spin. There are only two ways an electron can spin. And I forgot my basketball. All right. I always joked I was going to go and do this on my sabbatical. So the Harlem Globetrotters, right? These guys could spin a basketball on a finger. So this is not the direction the electron is going in its orbit. This is like the spin on its axis. So you can spin clockwise or counterclockwise. It doesn't matter which way, but it can be one or the other. So it's a spin on its axis. So there's only clockwise or counterclockwise. There's only two possibilities, which means there's a note there that says the Pauli exclusion theory. Since there's only two possibilities, two electrons can occupy any orbital. This is the piece that's a huge leap. So if I spin Tiffany clockwise and Tatum counterclockwise, they can be in the exact same place at the same time, and they don't run into each other. But they're spinning so fast because they're electrons. And that's what this is all talking about. The thing with this is these electrons are not moving in those nice little circles. They are waves. That's what I was talking about in the pre-lecture. Electrons do not move like you and I move. Electrons move in waves. And so if you have an electron, so the Tatum electron, she is actually a wave, and she is actually this whole thing at the same time, probably, because she's a wave. And if you're going, I really didn't like that wave part, you can always go back to that an electron is like a little bunny rabbit and it's running around a track in a perfect circle. You can always go back to that little comfortable place, and that's fine. It's all probability. All right, I'm going to share my thing again. We'll do this on paper. All right. So again, the shell is the N, and we'll call it the shell. Its original name was a principal quantum number. And again, this is always a whole number. As you increase the N, you increase the distance or the layer, and you increase the energy. So N equals 3 means you're at the third layer and you have an energy of 3. The subshell is the shape of the orbital. SPDF. We're going to add something here. I forgot to mention that when I did it up there. I usually have those 3 big boards that I get to work on and not a mess in my room. Somebody cleans up after me. All right, the orbitals are the path. of the electron, probably. So often we'll talk about electrons are not like small children. They're like teenagers. You never really know where they are. You know where they probably are. But, all right. Every subshell has a specific number of orbitals. So SPDF is the subshell. And every subshell has a certain number of orbitals. S's always can only have one. There's only one way you can draw a sphere in three-dimensional space. No matter which way you turn the basketball, it looks the same. All right, P, there's three ways you can draw a figure eight. You can draw it as an infinity sign on the x-axis, you can draw it as a figure eight on the y-axis, or you can draw it on the z-axis as another infinity sign. They're all infinity signs, actually. That's actually what the 8 came from. D, there's 5 possible ways to draw it. And F, there's 7. Now, this theory, it turns out, keeps going. It goes alphabetical after that. So the next one is a G, and there would be 9. And then H would have 11, and so on. It has to do with the limits in the mathematical equation. So you're going to see me write this again on the next page when we put this to the periodic table. Right now, what we're doing for 15, 20 minutes is we're just looking at the theory, which nobody ever likes. But then when we go back and look at it, when we do the homework, it starts making sense. So when you do the homework, do the best you can, make notes of the ones you want to definitely ask or listen about, and keep going on the homework. All right, the electron spin, 2 electrons per orbital. Wins a Nobel Prize. You don't need to remember this guy's name. There's so many different people's names. All right, so we're going to look at a type of question you might see in the study set or somewhere. So what is the maximum number of electrons? So this is the max, is the 2 electrons. So 3D. There's something else we have to add to this. I just realized. Well, D has 5 orbitals. And every orbital holds how many electrons? 2. One spinning clockwise, one spinning counterclockwise, never running into each other. And that is because electrons have a charge. And when a charge is spinning, it has a magnetic moment. And that means they can't run into each other. It's all about magnetism. And that is why everything's about to change, because we are moving into recognizing it's not about the electricity, it's about magnetism. And that changes everything over the next decade. All right, so 10 electrons. That's all there is. I don't have to see the math. I'm showing you the math. It'll be nice to have in your notes so you kind of get it. And again, it's going to take a lot of practice, so more than just today. That's what Wednesday's about. All right, 3D orbital. It has to do with the difference. This means just 1 orbital, so 2 electrons. So the subshell is all the possible orbitals. And actually, I'm going to flip pages. The very last page shows a picture of them in 3 dimensions. So this is what the p orbitals look like. They go along the x, y, and z. This goes into like 5th term calculus math. These are the 5 different d orbitals. And so, and then these are the 7 different f orbitals, what they look like. I put that picture in there because people always ask, oh, and there's the s orbital. It's an electron distribution probability, and it's based on they're moving as waves, not like you and me as matter running around a circle. All right, so the third principle in the third shell, so we have to go back, we have to add a little piece. That the n number also equals the number of subshells. So we'll do it with this example, and then I'll add more to it wherever you have space. So what that means is in the third shell, so when n equals 3, there are 3 subshells, 3s, 3p, 3d. Remember, everything has 2 pieces. They have a number which tells you which level you're at, and they have an SP, D, or F. So there are 3 subshells. If we were at n equals 5, there'd be 5 subshells. If we were at n equals 2, there'd only be 2 subshells. All right, we haven't answered the question though. Got that there's 3 subshells, but I want to know how many electrons. To get to the electrons, we had to go from the shell, figure out how many subshells. From the subshells, now we can figure out how many orbitals. Once we know the orbitals, we just double it. So S is 1, P is 3, D is 5. Again, that's the number of orbitals. SPDF, it's always 1357. That you end up remembering, even though you might write it down. So 1 plus 3 plus 5 is 9. So we have 9 orbitals. And every orbital times 2 electrons. So there's 18 electrons. That's a really tough question, but that's where it comes from. So you can ponder that. Again, don't lose sleep over it. Let's answer number 2, and then I want to go back and add a piece to this, and then we're going to put it with the periodic table. So this is all based on probability and possibility. So this one asks which are impossible, that they could not happen. There's no possible way. Actually, to do this, I have to go through that piece that I keep saying I'm going to go through. So it's taking this that the n number tells us how many subshells. So when n equals 1, there is only 1 subshell, and it is called the 1s. And yeah, when n equals 2, there are 2 subshells. That's what it meant. Again, it was all based off a mathematical equation. And so you always start with S. You always start with the lowest. So we always start with the simple sphere. And then we go to the next most complicated, 2p. There is no such thing as a 2D. Cannot happen. So another way I talk about it, this was the floor of the apartment. We're on the first floor, the second floor, the third floor. So right when n equals 3, we have a 3s, a 3p, and a 3d. The SPDF are the type of apartment that you inhabit. This is like the efficiency, the 1-room apartment. This is now like a 3-bedroom apartment. You've moved up in the world. Now we get to a 5-bedroom apartment. And then I don't know why you would want a 7-bedroom apartment. I'd be happy with 1 room, less to clean. Simple, neat, just move in a sphere. Don't have to think about a lot. All right, so n equals 4, it's the 4s, 4p, 4d, 4f, and so on and so on. There was something I was going to say. Oh, questions. Again, remember Niels Bohr said, you should all be going, what did she just say? So the question that I always love when I get it, which is once in a blue moon, which happens this month, is if we remember this is a p orbital, right? Well, what's there in the center? That's the nucleus. How can the electron go through the nucleus? Because it can't. It can never go near the nucleus. And the reason it can do this is because it's waves. So because it's a wave, it doesn't go through the nucleus. It is probability waves. So the electrons are probably out here. This is where it gets even weirder. And you can just go, I'm going to go back to that figure 8. I like that. That the electron is here and it's here, but it's never in the middle. Because it's a wave. It can be in 2 places at once. Right. And that's why Niels Bohr said, if you think you understand this, then you sure as heck don't. And that's because we're trying to think of it as if it's matter, and it's not. The electron does have a mass. It's extremely small. It's that verge of vibrations becoming matter. The thing that is real, and this is where once you can flip your thinking, it changes everything in your life. You're actually vibrations becoming matter. And the way we are brought up for some reason is to believe that we're material beings and that we influence the vibrations, but it's really the other way around. And that's what quantum mechanics is all about. All right, and that's actually what the ancient meditators and people who pray for a long time, that's what they realized too. We're going to put this to the periodic table. And so in class, I always gave out a hot pink periodic table. And I thought of this morning, Brittany, because she was having trouble finding her periodic table the other day. I recommend you guys get a periodic table that is like some bright color, or that you put it up on the wall so it's there. And actually, I think it was Tiffany said she laminated hers. I actually put one on the next page because I'm going to be writing notes. And I figured that would make it easier and to help you write notes on it. All right.
Brittany's asking, what's the Paul theory?
It's the what?
The Paul theory?
Pauli, sorry, I threw my piece of paper down. That was the 2 electrons, Brittany. This Pauli exclusion theory is the 2 electrons. That's all it is. There's a lot longer. You can Google it and get this long technical thing. This is it. My brain is really simple. That's why I got these squid eyes like this. So I have to simplify it so that I can get it out my mouth somehow. All right, we're going to put this to the periodic table. So we're going to draw electron configurations. We're going to start with hydrogen. We'll probably get to gold's on the homework. We'll get somewhere down below. There is going to be a shortcut about halfway through, so just kind of go with me. And it eventually clicks. It will click for some of you tonight, and it can click for all of you. I'm more anxious than any of you about this because I've always been able to talk to students one-on-one really easily, and it can take me 1 minute to get it to you. But I have confidence that we can make this work in this environment. All right, so this is the practical use of it. The theory, again, the mathematical equation was not written to explain the periodic table. He wrote it to explain how electrons behave based on all these experiments that were done with electrons. And when he came back, this is in the 1930s, Schrodinger, they said, hey, this explains periodic table. And yeah, most of these guys spent their whole life trying to disprove it, and everything they did would only prove it even more. So we're going to start with hydrogen. And we don't care about the mass. The atomic number is the number of electrons is what we're going with right now. And we're going to do 2 different types of electron configurations. So I'm going to do one, and then we'll go back and add the second one. So the first type is called NLX. There are all these different names for it. And I don't even know all the different names. And so since your teacher is the one who writes your worksheet, your SS, your WS, your exam, your extra credit, I just keep calling it this. So we'll just be consistent. So the N stands for the shell. The L is actually, this is a cursive L, is the designation of the subshell. And the X is the number of electrons in that subshell. And you will see as we go through this. So, we're going to do also what is called ground state. Everything we do will be ground state. I think there's a question on the review where I do an excited one, and you can make anything happen then when they get excited. That's when you see all the cool colors. That's where fireworks come from. But ground state means you always start at the lowest number possible. Which means we always start at 1, S. So we keep it simple. So it's 1s. And there's only one electron. So we write a 1. And that's it. It's really simple. All right. Now we'll do helium. There's 2 electrons. So we still say 1s, and we put 2 electrons in there. Now, the problem is we can't cram another electron in there, like when we get to lithium. And this is back to the question Brittany had asked, that Pauli theory. 2 electrons per orbital. S has only 1 orbital. So I don't have to keep going back and forth between these sheets. I'm going to write my little handy dandy thing over here. SPDF. Like in the past, students always would write this on their periodic table. But by the time you get done with your study set, by the time Wednesday's over, this will be ingrained in your brain like Avogadro's number. Still write it down, because when people are taking exams, they do funny things with their brain. But this, again, is the number of orbitals. And S has only 1 orbital. And every orbital can hold 2 electrons, so I can't fit any more electrons in there. So once the 1s is full, I have to go to the 2s, and I put 1 electron. These superscripts have to equal this number. So this 3 is the sum of the 2 plus the 1. All right, we're going to start skipping. So you want to do boron or carbon? Try and decide. You can do carbon. So carbon's number 6. The mass number doesn't matter because what does the mass number tell us? Here's the bonus question to make an answer. But not Kristen, because you already got a bonus point. What's the mass number tell you? And why don't we care about it here? So you have to answer both parts of that. Anybody?
Brittany says number of protons. Hold on. Number of no and protons.
Neutrons and protons. And why don't we need that for this, what we're doing?
They're in the nucleus, and we're talking about electrons being in the orbitals.
We are talking about electrons. We don't care about the nucleons. So there you go. I'm going to give to Philip because he's never answered me before. So I'm thrilled when other people answer me. All right. So for carbon, we start 1s2. They all start there. The only one that's not 1s2 is hydrogen. And then we go 2s2. And then we do not go 3s2. Remember when n equals 1, there's the 1s. When n equals 2, we have the 2s and the 2p. So that's where we're going next. After the 2s, we go to the 2p. And Philip, how many electrons do I put in there?
2.
Yeah, why?
Well, I mean, I kind of looked ahead and at the back of the lecture, and I saw the S block and the D block and the P block.
Oh, no, don't go there yet. We haven't gotten there yet. 2 plus 2 plus 2. We're adding up these numbers on top. The 2, the 2, and the 2. They have to equal this number. So that's how we get to 6. So let's do oxygen. So that's to get to 8. So all of you know, where do we start? So if you come to my office hour on Wednesday, don't say, I'm totally lost. Show me what you do know and say, okay, I get that. I go 1s2, and then I don't know what to do. So that's great. I at least know we got that piece down. There's going to actually be a different place that we start. As Philip was alluding to, but he didn't know that. And then after 1s, we go to the 2s. And then this is the piece, and don't answer it. I want everybody to have a moment to think. How many electrons do I put in my 2p? I'm going to put 4. Because 2 plus 2 plus 4 is 8. So again, these numbers up here have to equal this number down here. So why can I put 4? I'll give Brittany a chance to finish her point if she wants. So why could I put 4 in that one? Did she get it, Tiffany?
She wrote to get to 8. I had a different answer though.
Yeah, but all the other ones, I stopped at 2. But with this one, I went to 4. Go ahead, Tiffany.
I'm assuming because n increased, the distance is increased, so you can
Not
increase
quite.
the distance in that one. She says P can hold 3.
P can hold 6. So you're on the right track, Brittany. P has 3 orbitals. That means it can hold 6 electrons. So D can hold 10 electrons. S can hold 2. So some people will write this. This can hold 2 electrons, 6 electrons, 10 electrons, 14 electrons. You can put that like in your notes, but in all honesty, you don't need that by the time you get this because you can all double in your head, I'm pretty sure. So P's can go up to 6 as the superscript that we write. So, all right, we're going to do the other form. And my other notation, so this is called NLX. Or that's what I call it, because that's what it looks like to me. The other one, I should change the name since I have that power these days. It's traditionally called box and arrow. So again, these are electron configurations. You're always going to show me both. The box is the orbital. So for S, we'll show 1 box. So here we would show 1 box. And the arrow is the electron spin. So you can either spin clockwise or counterclockwise. Arrows either point up or point down. There's only 2 possibilities. You can't make your arrows do other stuff. This is how it's done. It's all you can do. Now, when there's only 1, it has a choice. This depends on your attitude. You can, when there's only 1, it has a choice. It can be up or down. It can't be both. When we get to helium, there's a shortcut here. You can show a box or you can just show a line. I'm going to show a line because the boxes get tedious. 1 arrow points up, and one arrow points down. So that's how we show 1s2. And again, you can draw boxes or you can just show a line. All right, so when we get to the next one, this would be my 1s, has 2 electrons, and then we show a space, and this would be my 2s. I'm going to label underneath for clarity. You don't have to label underneath since it's labeled right here. So this is my 1s, this is my 2s. My 2s just has 1 electron. One other piece for you is chemistry professors always make half arrows. I honestly don't care if you show a full arrow or a half arrow like I did there. If you look online, they're going to show them as half arrows. It doesn't matter to me. So you can either show a box or you can show a line. You don't get to make up your own like format. All right, so let's see what happens when we get to P. I'm going to go back to boxes and then I'll go back to lines. Because there's always somebody who likes the boxes. Again, 1 arrow up, 1 arrow down. Once you have your 2 electrons, 1 spins up clockwise and 1 spins counterclockwise. And when you get to the P, if you show it as a box, you show it as a long rectangle. Remember, it's a 3-bedroom apartment. So it's one apartment called the 2P, and has 3 rooms, 3 orbitals. Now, this is a rule. Hopefully you did this in pencil or you're going to scratch out. And this is Hund's rule. These are rules. I don't know why it's a rule and not a law, because I've never seen this broken. Electrons are like teenagers. They don't want to share rooms unless they have to. So here they had to share a room. They are not like small children. So a lot of you have small children, and small children love to sleep in the same room. So if they have the space to spread out, they spread out. The 2p2, these electrons will each get their own room, but there's a but. There's always a but because it's chemistry. Once one of them spins clockwise, the next one has to spin clockwise in another room. They do not share rooms. They can be next door. That doesn't matter because they're just different directions. They have to spin the same way, and it has to do with laws of magnetism, how magnets work. And let's just keep going, and you'll get this. You'll see the rules. It will work. And we'll get to the shortcut that Philip alluded to. If you want to show lines, there's my 1s. There's my 2s. And the 2p's, you show the lines close together, but with a space, and then you bracket them. I'll show you all different types of brackets, but you're showing me those 3 go together. They are all equal. The thing that is different about them is one is along the x-axis, one is along the y-axis, and one is along the z-axis. So this is how you fill in 4 electrons. And again, you're going to get the hang of this. We got 35 minutes to go. We got lots of time. Lots of stuff with this. They each get 1 electron. They all spin the same. So either all 3 are up first or all 3 are down. Then the 4th one has to partner up. It doesn't matter who you partner it with, but it has to spin down. So I'm going to be boring. I always go back to the first one. What would be wrong? I'm going to show it wrong next to it. This is wrong. It never does this. Even though this is not a law, it's just a rule. This never, ever happens. You would never get this. They don't pair up with an empty space in the same subshell. So the key is, because they're in the same subshell, this cannot happen. They each get 1. It has to do with their negative spins. that they will all spin the same direction. Yeah, gets into magnetism. All right, we're gonna skip to, do you want to do, let's do sodium. I'm gonna show you the shortcut. I'm gonna first show it the long way. It's up to you if you want to write it both ways. You might want to. We'd write 1s2, 2s2. Oh, sodium is number 11. Again, this is why you want to be familiar with the names, because when I'm writing symbols, which is all I do from here on out, and saying the word sodium, that you're able to follow that an A means sodium. All right, we have to get to 11, because that's the atomic number. So 1s2, 2s2, 2p6. That gets me to 10. And this is going to be the shortcut that I'm going to show you in a moment. So the next one goes to 3s. That gets me to 11. So the shortcut is 10 is a special number on your periodic table. Why is 10 a special number on the periodic table?
Because it's a noble gas.
Who said that, Kristen?
Yeah.
Okay. It's really weird. Sometimes you guys pop up and sometimes you don't, because I can only see 3 people. Yeah, noble gases. Why does that make it special, Kristen?
Because it's non-reactive.
Yeah, so they are stable. So there is a shortcut, and I'm going to start using the shortcut from here on out, because you can see this gets really long. You can always start at number 1. When we get down to lead, that's going to be a lot of writing. It's going to take up a whole page. Or you can start at a noble gas. So we're going to start at noble gas. There is a rule with the noble gas, with the periodic table. You can only move forward. You can't back up. So, comment that I made, I'm pretty sure I made in this class. Periodic table is actually 3-dimensional, and we flattened it onto this piece of paper. It's like the planet Earth, unless you're one of those flat Earth people. We have a discussion about that. It's fascinating to me that there are people out there still. So the neon, the next one is sodium. So you can do the previous noble gas, the noble gas that comes before it. And I'll show you the trick. It was written all over this one. And so we would say neon, and then we say 3s1. So how you're going to know how to do it? There are periods, which are the rows. So 1, 2, 3, 4, 5, 6, 7. Don't you love how I have to count out loud? The first period is really short. These guys referred to the shell. So here we're in the first shell. And then what Philip was referring to is the periodic table. The subshells are on here too. Do them in pink. These first 2 rows are the S block. So they call it the S block. You don't have to write the word block, but this is the S area, the first 2 rows. And then, if you count from boron to neon, 1, 2, 3, 4, 5, 6. 6 is a magic number. 2 is special because S holds 2 electrons. 6 is special because P holds 6 electrons. So from boron over to the noble gases, this is called the P block. And these are straight up and down blocks. Same with this. And then if you go here from scandium to zinc and count across, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It is 10. You can count. Most people count because they don't believe me yet. So from scandium, these guys are called the transition elements because Ds do something really funky. You're gonna love what we're gonna do with the Ds in a few moments. That's the D block. Oh, what a bummer. All right, if you count across the bottom, you're gonna get 15. You're going, what the heck? She told us it should be 14? Because I just randomly picked the periodic table and I didn't look for, there was, about 10 years ago, they decided the periodic table looked different and then they were wrong. And now these are the ones, yeah, everybody goes with it. But look, for all of you who said this periodic table, it has the OG. Remember that bonus question? They gave everybody names. They're actually down here now. All right. LA and AC actually belong up here in the Ds. So if you start with thorium and cerium and count across, this is the F block. Isn't that cool? So if you remember, when I said the first day or the second day, look at that periodic table. After this week, it never looks the same again. When you come for the midterm, right now you're going, whatever, I'm totally lost. Because you should be, because Nels Bohr told you should be lost. You should be questioning this. But really, by next week, you will look at that, and it should look like the midterm is, again, called a celebration of learning. Because you guys should be looking at a periodic table going, yes, I know what those numbers mean. And I know what these numbers mean underneath the elements. And now I see there's these blocks that explain how the electrons behave. Yeah. And the nucleus, we've done a lot. It's only been 2.5 weeks. You getting this much information in all your classes? They should like. All right. The thing that's nice about the shortcuts. So here's sodium. The noble gas that came before it was neon. And we often, I like to write the number 10 there. And then I come down here to 3. Yep. Yeah, I know. I wanted to finish my thought. And so for sodium, we start the previous noble gas. We go to the third row. So I write 3. And then I'm in the S block, and I'm the first box. So 3S1. We're going to do a bunch of these. And then you only have to show after the noble gas. You don't have to show all of these like we did up there. 1 electron. All right, I know that was Philip. What was your question, Philip?
So I think you mentioned this before, but I just want to clarify. Did you say that we can either show the LNX configuration or the box and arrow, or do we need to show both?
You're going to always show both. You're going to always be asked to show both because they each show us a different piece of information. And I think on the homework, there's only 4 of these that you draw out. And on the worksheet, it might be like 2. But you're going to be asked a whole bunch of questions about other elements. And so they each can get you to a different piece of information. So yeah. What I said is you can either show it the long way or the shortcut, but I would actually prefer, what I have found is the students who learn to do it the shortcut, they get it. And so once you get the shortcut, let's skip over to silicon. Back to green. So silicon's Si, which is number 14. And I know the numbers are small on this periodic table. So hopefully you have your nice big one. And we're going to do the shortcuts. So we find silicon, which is right here. The noble gas, you can't go backwards. You have to start with the one that came before it. So we're going to start with neon. Again, if you come to an office hour, don't tell me you're totally lost. Say, I can find the noble gas, and then I don't know what to do. Or say, I don't know how to find the noble gas. So come with a specific question. So again, silicon, noble gas comes before it is neon. Neon is number 10. Now you just have to know how to count. The number that comes after number 10 is number 11. Now we have to walk our way to silicon. So you can't jump from 10 to 14. Noble gas, then you have to go through them all. So after the noble gas, and this is why you want your periodic table number down, we're in the third row. And the way we're doing it, you're always going to be in the S block after the noble gas. So we're in the 3S. These are the 2 S's, 4 S's, 5 S's, 6 S's, 7 S's. All right, 3S, and we have to fill in both of them. And then we jump over here. And if you want, you can number your periodic table on the other side too. Because now we're in the P's. And it is the 3 P's. Still the same row, 3S, 3P. And I'm 1, 2. So you count your boxes, 1, 2. And then you check your math. We had 10, that was neon, plus 2, that is 14. We're good to go. All right, now back to what Philip just asked. Yes, we're gonna show it both ways. We're gonna show, this is the NLX. You show, and then we're gonna show the box and arrows. So S, just one line. Again, the box or the line, I should call it line and arrow. It would just make my life easier. So that's my 3S. You don't have to label your line, but you can. And then the P. And you can bracket the P. I'm going to show you different ways you can bracket it. Some people like brackets like that. 2 electrons. What's the rule about 2 electrons in the P's?
They each get their own box.
They cannot be together. So they each get their own room and they have to spin the same way. So they either both spin up or both spin down. So you can show them in whichever 2 boxes you want. And you can show them as half arrows or full arrows. Now, I have a question. Actually, let's do one more. I was going to do 2 more. And do sulfur. So go ahead and try sulfur. And then I'll ask my question. So we're going to do sulfur. And we're going to do potassium.
I have a question.
So you guys can try those if you want while I answer her question. Olga, was that you?
Yeah.
Go ahead.
Didn't you say that the arrows in the 3P, they have to be one apart if there's a space apart?
They can't be in the same room. They can be, these are just arbitrary rooms. They don't, I just was playing with them up here.
Oh, okay.
You can put them in the second and third room. You can put them in the first and third. You can put them in the first and second. They just cannot be in the same room, and they have to spin the same way.
Okay, thank you.
Yeah. No, thank you. That's actually really important. All right. Sulfur. Noble gas would be neon. Again, I think it's really helpful to write neon's numbers so you can check your math. After neon, you're down here to the third row. So 3S2, and then we cut over to 3P, and it must be 4. Because 2 plus 4 is 6, plus 10 would be 16. And what Olga was asking, you can have the space empty, or you can put them next door to each other, because they're not. They're along the X, Y, and Z axes, which are all next door to each other. There's no way we can show X, Y, and Z in a 2-dimensional piece of paper. And so you can ponder that. All right, so there's my 3S. And here, I'm going to show you. That's how I bracket. I had a class 10 years ago, best class I ever had, and they did not like my brackets. And so you can make your brackets however they want, but you're showing me that those P's go together. Now I have to put 4. They each get 1. And then one of them gets the second one. So back to like what you just asked, Olga, it doesn't matter which one gets the second one. You can put it the first one, you can put the second one, it doesn't matter. But only one of them is paired, so 3 of them point the same way, and then one of them points the other way. So, yeah, let's do potassium. Where do I start for potassium? Argon. Potassium's 19. The noble gas that comes before it is Ar. And after argon, we come down to the fourth row and 4s, and just one. So argon was 18. We just need one. S's are always going to have two, except for the one, this first row. And this is really nice because, whoops, teacher messed up. Just one electron. So this is the question I wanted to ask. What other ones that we did look like potassium? Well, the sodium, right? It has the one electron. And the lithium. It had that one electron. And if we look on the periodic table, there's a question on your first study set. What elements behave the same? The same family. And it turns out they knew that like almost 100 years before they figured this out. This is why they behave the same. If we look at silicon and sulfur. Sulfur and oxygen are in the same family. And if we look, they both ended up with this configuration where they had in the p's 4 electrons. And we can do the same with the silicon and carbon, right? That they both had these 2 unpaired electrons. So that's the next piece I want to add to this. This is 2 unpaired electrons. It is a question you will see. How many unpaired electrons? This has 2 unpaired. They don't have somebody to pair with. Helium has 0 unpaired. It's actually special when you have no unpaired. Lithium would have 1 unpaired. Oxygen also has 2 unpaired. But these don't behave the same because how we got to the 2 unpaired was different. Sodium would have 1 unpaired. Sulfur again has 2 unpaired. All right, there's another question I have to ask with these. And that is something known as the HEO. This is like my favorite question. And I thought I came up with this acronym, but I didn't. Or actually, enough of us used it. And so HEO is all capital letters because it stands for highest energy occupied. I think there's only one P. I don't care. Orbital. So I want to be careful here. It's the HEO, not the HEFO. So it's not the highest energy filled orbital. It's the highest energy occupied. So what subshell, and it should have been the highest energy subshell that has occupation going on. So if we were talking about carbon, that would be the 2p. If we were talking about oxygen, it would be the 2p. So it's not that it's full, it's that it has something. If we're talking about sodium, it would be the 3s. For silicon and sulfur, it's the 3p. For potassium, it's the 4s. Now, the thing that's really cool is we can do that without drawing these. Kind of back to the question Philip asked. I am going to ask you to show both ways. These box and arrows are really nice for answering how many unpaired. But this other way is really nice because the last piece tells us the HEO. It's also called in some places the defining orbital. But if I asked you for calcium's HEO, you should be able to answer that a snap of a finger because hopefully you all know calcium is Ca. And if you number down your table, this is from somebody's exam, it's in the 4th row in the S block. So this is my S block. So we would say calcium's HEO is 4s. If I asked about arsenic, hopefully you know arsenic is AS. And you would go again, 4s. I'm sorry, 4th row, and this is the P area. So you would say, oh, 4p. It's in the 4p area. And that would be its HEO. All right, we're going to do something in the D's. You ready? Pick your favorite D orbital. Let's do V for Valium. My purple pen, there it is. You can do V for Valium. V is number 23. And we're going to start with, so don't be like, I don't know anything she's doing. Say, okay, I can find V. V is vanadium, by the way. Vanna is the goddess of vowels. And so if you want to buy a vowel, buy it from Vanna. Vanna is the goddess of something. You'd have to Google it, and that's what vanadium was named after. Valium is not on the periodic table. Valium is a chemical compound made up of carbon, hydrogen, oxygens, and nitrogen. You can start with argon. This is great. I can't see you, so I don't know if you guys are totally lost or if you're all trying it. I'm going to pretend I can live in my own quantum world and you're all trying it. Or you can be on your cell phones. I wouldn't know that either. All right. And then we're in the 4th row after argon. And we say 4s. Now, hopefully you didn't rush ahead. We say 4s2, and then it's 3d3. And why is it 3D? Because that's how it is. So remember when I wound up Tatum earlier and put her in the 3D? The order they fill the orbitals has to do with their energy. They don't fill a full shell. They fill based on the energy of the shell plus subshell. These two pieces go together. So always you start at 1s, and then we go to 2s to 2p, and then they go to 3s to 3p. And then it goes to 4s, and then it goes to 3d, and it's like, oh my God, how am I going to remember that? And then it goes to 4p, and then it goes to 5s, and then it goes to 4d, and then it comes to 5p, and it's just like, what the heck's going on? And then there's all these cool like tricks online. You don't need that. All you need is this. It's all on your periodic table. Your periodic table shows you from the lowest to the highest. The S always goes with whatever row you're in. So the row equals the shell for your S's and P's. Always works. You don't have to memorize anything. You don't need any of these fancy charts. And it's easier to learn it and be able to do it. And then the D is always one number off. So these are the 3 Ds. I should have done that in pink. And it is because two things determine the energy. So even though the 4s would be bigger, it would be another layer out in my drawing. If I made Kristen run a 4s path, she's running a bigger path back here, right? So Kristen's out here running on this path, and it's this huge path. This is our 4s. But poor Tatum, she's in here doing this crazy 4-leaf clover path. So even though the 3D is a smaller orbital, that four-leaf clover makes it have higher energy than the next S. So on the periodic table, this was already designed, and somebody did math, and then it all fit together. Because that's how the laws of nature work. All right, this will be the 4Ds starting with Yeti, Deuterium, the 5Ds, the 6Ds. The Fs you're going to love. These are the 4Fs and the 5Fs. Fs are 2 rows off. Gs are 3 rows off. They're going to get to the Gs. The first Gs are the 5Gs. This is something Philip alluded to, because half of you would have found this online. There is this chart that shows this. But if you can do it without looking at this, I have that there so you can look at it. But I think if you can do it with just the periodic table, then you've got this. Let's do these orbitals, and then we're going to do a bunch of random ones and see if you got it, or a couple of random ones. For the S, one line, this goes back to 1357, 2 electrons. So this is my 4S. The D, you do 5 lines. So the number of orbitals is the number of lines you're going to do. So 1, 2, 3, 4, 5. Bracket the 5 together. Now, this is back to the question Olga just asked me. You have 3 electrons. So these 3 electrons go in these orbitals. They have some rules. There's a couple different ways you can do them, and there are some ways that would be wrong. So they all have to go in separate orbitals, but it doesn't matter which orbitals you put them in. So you can go 1, 2, 3. You can put them in any 3 you want. They just can't go in the same one as long as they can go in different ones. And they have to all spin the same. So that was what your question was, Olga. You could put them in the first, the third, and the fifth. It doesn't matter. You can put them in 1, 2, 3. You can put them in 1, 4. You can put them in 3, 4, 5. They just have to be in separate ones if they can. And they spin the same. It has to do with laws of magnetism. They all are equal, and that's why they have to spin the same and occupy different orbitals. All right, I'm going to do more. I'm going to flip this over. I'm going to give you 3 to try, and I recommend trying it like with your periodic table that you have, but you can always look at this. Let's do iron. Fe's number 26. Let's do those. So go ahead and try them, even if you only do the first step. And then do both methods. So you're doing NLX and you're doing box and arrows. And please do the shortcut. I'm doing the shortcut. Please do the shortcut. Then you're going to also tell me unpaired electrons, or I'm going to go through this, and the HEO. And there's one, oh, sorry. All right. So do the NLX, the box and arrow, unpaired electrons, HEO. These are just numbers. We're going to do one other thing because I have to remember to talk about this. I don't think if there's anything else. All right, try those for a minute. I guess if there is something, we'll do it in the homework. Oh, I got it. Or you can ponder this periodic table. This one actually makes a lot of sense. The spiral. My students last year did not like the spiral periodic table. I like this power that I have to mute you all, because usually they're complaining by this point. If you have a question, ask. I'm going to go through it. Find my eraser. When we get done, remember I do stay after, so if you want to check your worksheet or have questions on the WS4. Right. This is really cool. This is quantum mechanics. So if somebody's annoying you or asking you, what are you doing? Be casual and say, studying quantum mechanics. Which you can't understand, because nobody can understand. It's really cool. All right. You want one more minute, or you want to just go for it? You can keep doing it. So the starting point for each one of them is the previous noble gas. So bromine, you can't start at krypton and back up one. You have to go to argon. So questions with that. So you find your element, go to the noble gas that comes before it, and you just have these huge periodic tables that I get to climb up to for doing this. All right, so we're doing iron right here. Start with argon, comes before it, and after 18, you come to 19. It says we're in the 4th row, and you're always in the S block. So we're going to say 4s2. And then this is the Ds. And you can count 1, 2, 3, 4, 5, 6. You do count the box you're going to. And all you have to remember about the Ds is they're always one. Their shell is always one less than the row number. So that's what this is showing, that after the 4s, you're in the 3D. But you do want to get to a point where you can understand this, because your exam does have a time limit. It's usually a pretty generous one, but if you're trying to it's not going to be generous if you don't study and understand this. Plus, it's really cool to understand this. Right, and this adds up. 18 plus 2 is 20, 26. 4s. You don't have to label your lines. I just do, to be clear. 5 lines, because D's always have 5 lines. This is again the 3D. SPDF are lowercase letters. 6 electrons. Each box, each line gets 1 electron. They all either spin up or they all spin down, the first 5. And then number 6 pairs. Again, back to the question Olga asked. It can pair with any of them, but one of them has a paired. So unpaired is 4. You're not going to be asked how many paired electrons. You're just going to be asked how many. So how many electrons don't have a partner? So actually, I'm going to flip back to the other side of my paper, because I just realized a question. It's not asking, like for carbon. Carbon was only 2. I'm not asking how many empty spaces I have. We don't care about the empties. It's just asking how many arrows don't have a partner. So it's not asking how many empty spaces. So 4 unpaired. The HEO is the last piece. So the 3D. So the valence. Valence here is 8. Valence electrons is everything after the noble gas. They are the electrons that react. So back to definition, I think it was Kristen who answered this. The noble gas is a shortcut. You can't start at oxygen. Oxygen is so freaking reactive. Did you guys notice in the homework, oxygen was in every compound? It's pretty much because it's so reactive. You can start at a stable place. Everything else, the valence electrons are the reacting electrons. So valence is electrons are the outer shell. Electrons or the ones, the reactive electrons. They come after the noble gas. All right. And Katie, I know you're going to say, where's the question that we get to email you? I actually put it in the worksheet. I asked it in the video, and then I answered my own question. And then I asked another one at the end, and it's actually at the end of the worksheet. So you can just write it on the worksheet. All of you. All right. No questions. All right, bromine. We'd go 4s2. So again, after argon, we're in the 4th row. These are going to be the 3Ds. You can count, but we went all the way through the 3Ds. So there's 10. Ds can hold 10 because they have 5 lines. Each line holds 2 electrons. And then we're back to the Ps. Your S's and Ps are always your row number. And bromine's 5 boxes over because it's 1 from completion. This comes straight down. So 1, 2, 3, 4, 5. The staircase was the metalloids. So just be careful. And yeah, you would have to show me all these. This is my 4s. Bracket however you like. They're all paired. If you don't bracket, you're going to lose 110 points. The bracket is telling me you understand these 5 go together. And this bracket tells me you know these 3 go together. So these are my 4 Ps. These are my 3 Ds. 5 electrons. They each get 1. And so we have 1 unpaired. 4p is my HEO. Valence electrons, 17. There is an alternative answer, and that is 7. Once the D's fill, they don't react. We show them. But once you have 3D10, they basically don't react anymore. I accept either answer, and it has to do with different websites are going to teach it different. And also it's something I'm going to do after the midterm. All right, after krypton, we're in the 5th row. So TC is here, technetium, man-made, because 43 is an unstable number of protons. Can't make it. So krypton, then you come down here, you're at 37. So 5s is always just 2 electrons. And then we're in the 4D. Starting with deuterium, 1, 2, 3, 4, 5. So 5s, and then 4D, and then 5 electrons. And we're done. Other than showing this. So 5s, you show your 5 lines. Again, the lines equal the orbitals. Even if a line is empty, you show it. And the arrows equal the electron spin. These 5 all spin the same way. They're either all 5 up. Tell from my personality, mine's always spin up first. So we have 5 unpaired. This is my unpaired. My HEO, my last one, is the 4D. It's not the last full orbital, it's the defining, it's where it is. And the valence would be 7. And yeah, there's an alternative, an old way of numbering. So they used to call this the 7 Bs because of the 7 valence. They just changed the numbering. I think that's all I got. But again, it's cool. Just learn. So you can dream about electrons making quantum leaps. They can only be here or there. It's not like a mosey walk over. It's a jump. It's really cool. And it's all because they can only be at this vibration or that vibration. All right, I'm going to stop recording unless somebody had a question.
I do.
Go ahead, Olga.
What does HEOO stand for?
HEO. So highest, I always write both pieces. Highest energy. So we're filling, and actually, thank you for asking that. We always go from lowest energy to highest energy. There's something else I want to add, so thank you for this question. That's how the periodic table is arranged. So HEO is highest energy, and then it's occupied. Again, not filled, just it has an electron orbital. I want to mention something, and I don't want you to do it this way. I would probably mark it wrong, because it means there is another way on Google where they do it this way. And it really doesn't show you the same thing as this. This has much more meaning to a chemist. This must be a physicist's way. This is showing from inside to outside. It has importance for something we will do momentarily after the exam. But again, I don't want you doing it that way. In case you like Google and just want to copy everything off Google for your homework, that's not going to really help you learn it. Was there another question? All right, I'm going to stop recording and